Have you ever wondered why the basic building blocks of electronic music, those simple synth waveforms, all sound so completely different from each other? I mean, a sawtooth is super buzzy, a square wave is kind of hollow, and a sine wave is just, well, it's just pure. In this explainer, we are going to pull back the curtain and find out exactly why.
Okay, so here's how we're going to break it down. First, we'll look at the shape of sound itself. Then we're going to meet the purest tone, which is, no joke, the key to everything else. From there, we'll uncover a sound's unique fingerprint, which lets us put together the classic harmonic recipes, and finally, build our starting palette for making awesome sounds.
All right, first up, the shape of sound. So what even is sound? Well, at its most fundamental level, it's just vibration. And these things we call waveforms, they're basically the blueprints that let us see the shape of that vibration as it moves through time.
So when you see those squiggly lines on a synthesizer or in your audio software, you're looking at a waveform. It's literally a map of that sound's vibration, how the air pressure is changing, or how voltage is zipping up and down inside a circuit. It is the visual DNA of a sound.
And that leads us to the big question, right? The central mystery for this whole explainer. If a sawtooth, a square wave, and a triangle wave are all just repeating patterns of vibration, what's the one crucial difference that gives each of them its own unique, distinct voice? Let's dig in.
To solve this mystery, we have to start with the most basic, most fundamental shape of them all. Seriously, if you understand this one, you have the skeleton key to understanding all the others. We're talking, of course, about the sine wave.
The sine wave is just pure. It's the simplest, smoothest, and cleanest of all the waveforms. This is sound boiled down to its absolute essence, just a smooth, clean wobble. You know that sound a tuning fork makes? Yep, that's a sine wave.
You see, a sine wave is what we call the fundamental. It's just one single frequency with no extra bits and pieces tagging along for the ride. It's the smoothest possible way for a vibration to happen, and that's why we call it the atom of sound. Because, and this is the really cool part, you can actually build every other sound in the universe just by stacking a bunch of sine waves together. So here's the absolute most important thing to remember. A sine wave is just one single frequency. If you play a 440 hertz sine wave, the only thing you hear is 440 hertz. Nothing more, nothing less. And that is both its secret and, in a way, its limitation. Okay, so if the sine wave is so perfectly simple, where does all the character, all the color, and all the richness of other sounds come from? Well, that brings us to a sound's unique fingerprint, the secret of harmonics.
Harmonics are the secret ingredient. They are these little extra frequencies that are basically piggybacking on top of the main note, the fundamental. And they aren't random at all. They show up at these really clean whole number multiples of that main pitch. This collection of harmonics is what our brain interprets as a sound's timbre, or, its color and character. And the math behind it is so simple, it's beautiful. Check this out. If your main note, your fundamental, is 100 hertz, its second harmonic is exactly 200 hertz. The third, 300 hertz. And it just keeps going. It's this clean, predictable pattern that gives a sound its unique personality. And it's why a guitar and a piano sound totally different, even when they're playing the exact same note.
So you can really think about it this way. The specific recipe of which harmonics are there and how loud each one is basically the unique DNA of that sound. It's a sonic fingerprint that makes every single waveform totally distinct.
All right, we now have our atom, the sine wave, and we have our secret ingredients, the harmonics. So it's time to become chefs and look at the actual harmonic recipes for the other classic synth waveforms.
Let's kick things off with the triangle wave. It sounds really mellow and soft, kind of like a flute or a recorder. And here's why. Its recipe only includes the odd-numbered harmonics, so the third, the fifth, the seventh, and so on. But, and this is key, the volume of those harmonics gets quieter really, really fast, which is why the sound is just a little bit brighter than a pure sine wave. Now, this is where it gets really fascinating. A triangle wave and a square wave are made of the exact same ingredients, just the odd harmonics. The only difference is in the amounts. Think of it like cooking. In a triangle wave, the volume of those harmonics drops off super fast, making it sound soft. But in a square wave, those same harmonics are way louder and stick around longer, giving you a totally different flavor from the exact same recipe. And that difference in volume is what gives the square wave its iconic sound. It's hollow, a little woody, and very computery, like classic 8-bit video game music. Because those odd harmonics are so much stronger, it creates that distinctive, reedy character, which, funnily enough, is often compared to a clarinet, an instrument that also naturally has a lot of strong odd harmonics. And finally, we have the harmonic heavyweight, the Sawtooth wave. Its sound is buzzy, rich, and in your face, almost like a brass instrument. And its recipe? It's simple. It has everything. It contains every single harmonic, both odd and even. This makes it the densest and most complex of the basic shapes. It's a lot like the sound of a bow on a violin string, constantly catching and releasing. And look at that, this table just brings the whole story together beautifully. You can see the direct line from the harmonic recipe of each wave to the sound you actually hear. The sine is just the fundamental. The triangle and square both use only odd harmonics, but their different volume levels create completely different characters. And the sawtooth? It just throws in the whole shebang. This right here is the atomic theory of sound in a nutshell.
So that's the theory, but how does this all fit into the bigger picture of actually making music and designing sounds? Well, this is where we move from the why to the what and talk about your starting palette. It's really simple. Just like a painter starts with primary colors, a sound designer almost always starts with these 4 waveforms. They are the fundamental palette for a super common technique called subtractive synthesis. That just means you start with a harmonically rich shape, like that big, buzzy sawtooth, and then you carve away frequencies with filters to sculpt the exact sound you want. So there you have it. You know the secret now. The difference between a pure, clean sine and a rich, buzzing saw isn't some kind of magic. It's just a recipe of harmonics. You basically understand the atomic structure of sound. So the only question left is, now that you have the building blocks, what are you going to create?